Okay, we are recording. Okay, good evening, everybody. So what I'll do is, so yesterday, last time what we did was, if people recall, we did temporal difference learning, right? Temporal difference, which was to estimate a value function v pi for a policy, for a policy pi. This is what we wanted to estimate. And what did we do? We said that we did not. So people who are following the transition matrix and the reward function, that is the model of the environment. Unlike in the past, is not known. So we said that since it is not known, we will do Markov chain Monte Carlo. So Monte Carlo estimates is what we were doing, that we were traversing the MDP and we were trying to get the rewards and the transitions, because we saw that the expectation can always be by law of large number written as a sample expectation. So the Monte Carlo estimate is based on sample estimation of expectation. Anywhere there is an expectation, we can use data to compute empirical averages. So what we saw was that anywhere there is an expectation, anything that is available to us in terms of expectation, we could write it in terms of sample expectation. That is sample or averages. That is 1 by n summation of FIs. So that's like just the empirical average, like we normally write. So now we could see that we were able to find out the policy or the value function. The policy is given to us, the value function based on how we traverse the environment. So the value function for that policy is known to us by just traversing the environment. Just if you recall, so this is again, I keep reinforcing this thing, that this is the value function, that is the expected reward at state k. I keep drawing this, and then you go on till you reach the terminal state, and all the rewards in between you add. That's what your goal is. And you try to maximize the expected reward. That's all you want to do. And basically what we saw last time, I will show an alternative derivation for that. It's of the TD0 algorithm. So it's easier this way. So people, what can we write this as? We can write this as SK, AK, SK plus 1 plus, again, the same thing, I equal to, again, 0 to infinity, R of sk plus I plus 1, ak plus I plus 1, and sk plus st, whatever, k plus I plus 2, given sk, right? This is what we could write this as. So if we could write this as this, and then I kept telling you that, again, this inner value of the is not known to us. Therefore, we can again take an expectation by fixing sk plus 1 as s prime. Well, here we don't even need to put anything. You can just write sk plus 1 just as a dummy. So clearly this turned out to be the reward function. So if sk is s and this is s prime, so this turned out to be the reward function, expected value of the reward from s a s prime plus v pi of s prime. Yes or no? This is what we saw time and again. Because we did not know this, we just replaced this by the value function at the next step. So basically we do a dynamic programming where we at sk, the estimate of the value function of sk, we say, no, I do not know the value function of sk. So what? I will take the reward, whatever I get, and I will go to sk plus 1 and I will see what is its value function. And then just I'll add to it with the reward. This is basically a dynamic programming that you're doing, keeping on doing it, leaving it into smaller, easier problems that is you keep when you keep traversing. Why do we do that? Because we know at the terminal state, v pi of st, this is 0. This is the base case. So this is very important. This is the recursion. In terms of computer science, this is the recursion, or mathematics, this is the recursion. And in terms of algorithms, it's called the dynamic program. Anyways, so we got this equation, fine. So now I told you I don't have the model in my hand. So if I represent this as some function f of s a s dash, so anytime we have an expectation, say you have a function f, I will not put the parameters, whatever parameter you have, the expected value of that function given sk is equal to s, do you agree can be written as summation of this function f for I equal to 1 to n, for if you have say n realizations of this function such that sk was s. Yes or no? That's what we could write. So anytime we could do this, we have seen that we can write this as, so this is, say if I had the nth value function of the state sk, so I could write this as, what could I write this as? It's a general theorem. I'm just trying to say that I'm trying to come up with an iterative algorithm. So for any expectation, you don't even need to be sk equal to s. Say s expected value of this. Let's just write expected value of xi, right? So if we just have to write expected value of x, for example, all we need to do is expected value of xi by 1 by n. Yes or no? This is the nth estimate of the expected value. Do you agree? Fine with everybody? Yes. So I am saying this is the n sample estimate. N sample estimate. You'll see this will be very helpful for any expectation. This will become helpful because why? Xn dash can be written as 1 by n minus 1, n minus 1, 1 by n. This is just multiplying n minus 1 on both sides and then writing this summation as, I'll just rewrite it a bit differently this way, and I equal to 1 to n minus 1 xi. And what else is left? Xn. Correct? This is all what you have in hand. Correct? This is the same equation. I rewrote it. So this thing can be written as x bar of n minus 1, right? So you get x bar of n minus 1 plus 1 by n xn minus xn bar of n minus 1. Do you agree? This is what you get. Fine with everybody? So this is the random variable, yes or no? So this you could write as x any time. These are IID random variables, so I could write it at x instead of xn. This is my update equation. Do you agree? Yes. So we have derived it multiple times, but now why do I do this? Because anytime I have an expectation like this, I could directly use this lemma to find out a stochastic update. Stochastic update. So you tell me what is this update going to be like? So Vn of sk, what will it look like? This update for this expectation. This is just going to be this function f. So I will just copy paste the function.
Yeah, so it would be Vn plus 1 by n into r of Sn a n Sn plus 1 minus.
Not n k. We are finding for state k here.
Oh, sorry, I was.
Yeah, no problem. So Vn of Vn minus 1 of this equation again. So Sk plus 1, yes or no? Do you agree?
Yes.
Sk plus this is the function f that I have, f minus Vn of minus 1 of Sk. Yes or no? Correct? Exactly. This Sn minus 1, I put it here, and the x is this term. Do you agree? Correct? Okay,
Yes,
if
we
you have
got
a
this time by
yeah,
get
we by cut
normal.
by removing, yeah. We removed, added and removed some. This is called the TD0 update. And then we got multiple updates of this form saying that why one step, we can go 2 steps, 3 steps, 4 steps, 5 steps. And we saw that this term, which is known as the difference term, dk term, the difference, temporal difference term, could be for multiple differences. We saw that last time. So this is all what we saw from last time. So why do I show this derivation and why do I show all these things? Is because there is a what I want to portray to you is that these depend on the policy that you have selected. So today we'll be discussing without even selecting the same policy that you want to evaluate the value function for, we could still find the value function for that policy. What do I mean by it? Say one policy is dangerous for an agent. So I'm just not writing currently anything. I'm just telling a story. Say one policy is dangerous for an agent and you don't want that agent to play that policy. For example, in a self-driving car, you don't want a car to crash, but you also want the car to know what will happen if it crashes. So in those cases, we like to play safer policies or different policies which we have control over rather than the environment controlling it. And then learn the policy that we desire to learn. So that's the biggest goal of today's session. So instead of actually playing out the policy, which we are actually doing, yes or no? So you're here, what do I mean by playing out the policy? AK is selected by which? Selected according to the policy, right? You sample based on the policy, correct? The sample, the state, the action AK is selected based on the policy, yes or no? So I am saying that I am not going to, and this n goes to V pi. And it's the same policy that we are selecting actions by. I am saying I will not select actions by this policy. I will select by another policy beta. So that's the discussion topic today. And the question is, can we do that? It's a very, very interesting idea. But before we go into that, so TD lambda algorithm, as you can see, we have this entire trajectory SK plus 1, where every action is selected based on the policy. And we update the current state based on number of lambda to the power I temporal difference term. That is, at every step, you calculate the differences from the reward, next state, and the current state's value activation function. And then just you keep adding them. This will be one of your assignment questions. I will today show TD0 and TD lambda will be for your assignment, where you will have to vary lambda and C. I'm telling it beforehand for your second assignment, or I don't know how many more assignments I'll give, maybe one more. So that's the plan. So we derived all these, but we also know the value function currently. That is using the TD lambda algorithm. We know that. So we know that the value function V pi is the expected value of the reward S A S prime. Now we use these interchangeably, the stochastic update and the non-stochastic update. This is the one I know. Right now, if I have to find the optimal policy, so this is known. I know for a policy pi, using TD temporal difference learning or TD lambda, what can I find out? So people who are following me, what do I use TD lambda algorithms for? What do I use it to find? For policy evaluation, right? We see how evaluation, that is finding out how beneficial is a state or action under a policy pi? Yes or no? That's what we do in policy evaluation. We find out the value function v pi or s, which is a mapping from the state space to real numbers based on the policy. We try to see what is the expected reward from a particular state. Clear to everyone?
Yes.
So, but what is the actual goal of RL? Do you remember? What is the end goal?
To maximize long-term reward.
Maximize it. That is, find the best optimal policy. I kept telling it that control is the ultimate goal. What is control? Control means finding the best policy. We have found it using Q learning before. We'll see best policy pi star. Right. So, but can anyone tell me how do I use TD learning? So normally people don't use TD learning for finding out the optimal policy. They use Q learning itself instead, as we have done before. The Q, which does both action and state. But say we want to do using value, you don't have any other option but to use the TD learning. So can we use TD learning algorithm?
Like we did it policy evaluation and then policy iteration, we would just see the which action is giving me the maximum reward and then use that policy again and calculate v pi using TD algorithm, TD0 or TD lambda, and then again select the maximum action.
Correct. So, but there is a problem here. We'll see why. That's exactly the thought process you should have. Very good. So you say TD lambda algorithm you used, and for a policy pi, this is step one. So you evaluated the policy. So you got the value function. Great. Done. So once you got the value function, the step two is policy improvement, right? The T operator that we found out. In policy improvement, what do? We find out for all actions in the state space S, what is the action that maximizes the long-term reward? Yes or no? This is what we have to find out in the Bellman equation. Do you agree? Say you have to find out. Correct? For which action do you maximize this? Do you agree? Fine. So now I know this. I know this from policy improvement. Correct. But there is a problem here. Can you tell me what is the problem? The value, this is known, this is fixed now because I have done policy improvement. The reward function is unknown, right? Yes or no? Do
Yes,
you
we
agree?
were sampling the words. That's the
Exactly. So in a normal case, in a old days, in the few from initial lectures, this equation was equivalent to what? This equivalent was to argmax of all actions in AS, and we could sum over. So this function. You could take an action. So let's write it down again. Expected value of reward as AS prime. I don't know currently can't use this. So what will I have to do? We do not know S to S prime transition. So we will have to condition, yes or no? AK is equal to A, correct? And we have to take a expected value of A in whatever you have. Do you agree? This is all we had to do. So let us, for example, write it down. No? So V pi star is this. V pi star is this. So now I'm saying that this is not known to me. So I don't know the value of this. So I have to condition based on the action. Do you agree? Because the probability distribution is not known to me. Fine.
Okay.
Yeah. So now next, what do I do? So I get the inner summation as the probability. So normally what happens in Q learning is you already have this action given to you in the conditioning vector, right? But in V, when you're learning the value function V, that becomes a problem for the Bellman equation because you have to, anyways, you're maximizing argmax over this, over the actions. And you have this action space in the denominator, which does not make sense because this inner expectation, what does it become? This becomes S prime, S given A, and reward from S A S prime plus V of S dash over all S prime in state space. Correct. But there is a problem here because we also have to take an expectation over A because that's how we are defining the policy to be, right? So basically what is happening to here is just to bring in the expectation over actions over here, I am having to remove the expectation altogether. That is what is happening. But we could just not do that and write the Q function instead. I will do it a bit differently. So instead of doing this, I can what I do. So I'll not erase it. I can't do this because this expectation comes over A. So I cannot do this because I have to find out maximum over A, argmax over A. Yes or no? So I cannot really do this. So I have to use the Q value function. So Q pi of, so I know that a action A can be written as argmax of A belongs to AS Q pi of S comma A. Yes or no? This is this I can write for a particular state. Correct? This is not a problem. That is the best action. This is basically saying best action you select. You select. See, we do not know Q value function, but we know that this is basically the same thing, but we have the conditioning of the action given to us. That's the benefit of it. So this is the same equation because the Bellman equation will be still the same. But Bellman equation, when it's still the same, all the difference is that you have an action conditioning over the action. That's it. And we said that this could be written as the summation of S dash SA reward S dash plus V of S dash. And we said that we could maximize over an action. A belongs to X. This is what we found out, right? Do you agree? Fine.
Yeah, so we are
But
shifting from like one argument probability function to two argument.
so the model distribution itself was just S comma A, isn't it? The model's distribution was always we never had direct access to the Markov matrix, which was from a state to another state. What is the action? Based on an action, we knew what is. It's a controlled Markov chain, right? Yes or no? Because
Yes.
we know this under an action, what is the transition probability? Not directly. So I don't have a problem over here. Do you see that? Because I have access to this V pi, correct? And now I am basically sampling from this distribution. So a rough estimation of this could be this. You could basically write this. So if you have the estimate of the value function V pi of S dash, you could estimate the reward function, yes or no? Could you find out the estimate for the reward function? You could,
Like we
right?
would again do Monte Carlo sampling, right?
Correct. So for all states,
Like
perform.
this is like almost dividing our policies into like vector 100 or 0100 vectors, and then it's doing bandits only. But
Yes,
only
exactly.
the policy is a vector with 1 1 and all other zeros.
Correct. So you select for all the states, you perform this update. So you have a Monte Carlo for the reward function. So, but this you need to do only once, right? Because the reward function is not going to change based on the policy. So you select the first step, select an action and select the next step and see what reward you're going to get for all this triplet, correct? For the triplet, estimate the reward function, estimate reward function using Monte Carlo, correct? So this is a bit of a hassle, but you can still do it. So now you have access to the reward function SAS dash. For every state, you have a good enough estimate. So now when you do policy improvement, what do? You do pi star of S or pi n plus 1 of S as argmax over A in S. And you see, what do you try to see? You try to see the expected value right here. Correct? So you try to see the reward function, reward SAS dash plus V pi of S dash. And you sample it for every. So you do it for every A and S, and you take the Monte Carlo average of this. And you see which action maximizes this reward. Correct? Fine. So basically, every expectation that you have over here, the same expectation, you can clearly write it in terms of the argmax of this function. So this function is this is estimated using Monte Carlo. Using Monte Carlo, since you have already estimated it, you don't even need to compute it. So estimated using Monte Carlo, estimated using what do you use it? TD learning, TD lambda. So and then you get pi of n plus 1 and so you have an improvement and then you select the action. So you can keep on doing policy improvement like this as well. It's not a big problem. Okay, any questions?
Like here, the only function that we assume that is dependent on the policy is the value function, and all other rewards and the other condition are
Just
states.
depends on the environment.
Yeah, that depends on the environment, as it's in usual RL problems. And the goal we set out to prove is that whichever policy we take, we'll uh, end up at the optimal policy, just like in the
Correct.
other. Yes.
Yeah. So, but to avoid this cumbersome policy, we can do what is called as a Q learning. This is what I'll show now. We'll come to what is off policy and on policy now in a while. But to avoid this, what I'll try to do is I'll get this. Now, what I'll do is I will. So all the while I was trying to learn the value function, right? V of S. This was what I was trying to learn in TD for a policy pi. But now I say that this is cumbersome because I have to, at the end of the day, select an action. Select an action, which is my goal. And to fulfill this goal, I need a function that will be giving me the value like directly. Why not just do this? Q pi of S comma A. Learn the function directly is the question. So if you do that, you can write this again in terms of the expected reward from I equal to 0. Again, it's a stochastic shortest path problem. We are not going to do discounted mode. So these are just episodic tasks, I mean. ST plus I, AT plus I, ST plus I plus 1, given ST is equal to S and AT is equal to A. So you can clearly see it's the same equation again. So I will write this again in terms of reward of ST, AT, ST plus 1. So it's already given to me. So I can write S, A, S prime plus expected value of, what can I write this as? Summation of I equal to 0 to infinity. Reward of, again, I'm writing the same thing. I plus 1, T plus I plus 1, S T plus I plus 2. Given ST plus I, or ST plus 1 is equal to S dash. And all the conditions that were there previously. So again, this is the same equation, which says that RSAS dash plus this is V pi of S dash given ST is equal to S, AT is equal to A. So now Q pi of SA, just like an optimal policy, any policy in the optimal policy as well, the Bellman equation, it will hold, right? For optimal policy 2, it holds. Correct? So since it holds for any optimal policy as well, so how is the optimal policy V pi star related to Q pi star? How is it related? What do you think?
It was the usual Bellman equation only, just that for the V pi star, we would have written expected value of Q pi.
No, so this is very simple because for a particular state, if you already know for that state what actions, what is the expected reward you get for every action, you will always select the action with the best reward, yes or no?
Highest R max of.
Yeah, here it is the max because you are putting the value V pi. So that's what we say, that instead of learning the TD learning algorithm, we can clearly write down this equation as at optimality as max of A in S. Here it is A dash S dash Q pi star of S dash comma A dash. Correct? Given ST is equal to S, AT is equal to A. Fine with everybody?
Yeah, that's what I actually wanted to say, that
Yeah.
only we would be doing the usual Bellman equation, just instead of where the action would be stated as the max action for
Correct.
each.
Correct. That is then very good. So basically we can, this action will be basically written as the maximum value of all the Q value function. So again, if you have to write, so this, if you want to learn, say in a tabular manner, so tabular algorithm, I think we had not done. So I'll just write it down in a tabular manner. So for every state and action, if you want to write a loop and write it, what will it be like? Qn plus 1, tabular and model based. If it is model based, then we can write Qn plus 1 of S comma A as, what do I write this as? S dash in S, the probability distribution, reward as reward S A S dash plus max of A dash in A S dash cube N of. This will work. This is a Q learning algorithm that will work if and only if P dash is available. Yes or no? We have shown that Bellman equation converges during using the operators. But this will only work if this is available. If it is not available, what will I do? Not available. P of S dash SA. If it is not available, what will I do? Again, I told you we derived a function, right? We derived the theorem that xn bar is equal to xn minus 1 plus
Yeah,
1 plus the learning
just in
rate.
Monte Carlo.
Yes, we'll just do Monte Carlo. So we will write this as Qn plus 1 S for S comma A as, so let me write it down, Qn of SA plus gamma of the state S comma A for the n plus 1th visit. And then I write down the reward is AS dash plus C. I write down whatever is this there in this expectation. That's all I'm going to write down. Max A dash in AS dash Qn of S comma A minus Qn of S comma A. Do you agree? Not the prime. This is Q of S comma. So this is the next step, current state, and so on. Do you agree? Fine. Okay. So this is the update rule I have. So basically what you do at a step S, at state S, what will you do? Select the action based on the policy. Do you agree? Okay. So you can select epsilon 3D version of it. And then at S dash, what will you do? Select the best action. Do you agree? So you have a state S, you have an action A, you observe a reward R, go to a state S dash, and best A you select. This is the step that you will have to do to compute the Q learning algorithm as we have found before. Okay, so now we can clearly see that this next action that we select is based on another action. So selecting the best action is not the same policy. Not same policy I. And this comes to the discussion. Here we come to the discussion of off policy and on policy. This is an example of an off policy algorithm. What does all this mean? Because we are not selecting an action based on the pi always, this is creating a question of an off policy algorithm. What is an off policy algorithm? Let's try to look into it now. So we learned TD algorithm and found out the optimal value function using it. Next, using the Q learning algorithm, we directly found out the value function without having to estimate the reward and so on. We were directly learning the S comma A value function, and then we could just approximate the action, which is not very easy in doing in a TD learning algorithm, but both of them can be used with some effort. But now we saw that there is a problem in this entire thing. What can you tell me what is the problem?
Before that, could you please go to the last part of Q learning and explain what you wrote in green again?
Green, blue, you mean?
Sorry, blue.
So what do you saw this algorithm, right? So the algorithm is fine. We derived the algorithm.
I mean, just for practice, could we like write and tabulate the difference between uh, normal TD and Q learning once, like write the algorithm?
Sure.
Would that take?
Yeah, we'll do it. I have already written the Q learning and TD learning algorithm in the for demonstration today. So I think that will help. We'll see the Python code. But anyways, I'm showing what I'm trying to say. So this is the Q learning, right? model free. Do you agree? And for
Yes.
TD0 or TD0 algorithm, we can write Vn plus 1 as Vn of S, right? Plus reward of SA S dash plus Vn of S dash minus Vn of S. Correct? Fine?
Yes.
Okay.
In case of TD0, we are sampling the reward. But what are
Both
the
cases. So now TD0 originally is policy evaluation algorithm. Correct? So that is Vn goes to V pi as n tends to infinity. Clear? Fine.
yes.
Pi. So the action is being sampled based on the policy pi that you're selecting. Correct? Fine.
Yes.
Okay. In Q learning, pi is learned implicitly. What do I mean by that? See, you start with a uniform policy. Is 1 by n for say if there are n actions. I'm 1 by a, let us write. If there are a actions available. Correct. So, but then what do? You say you are in state S. Start from state S. Okay. And start from state S. I select the action based on this policy. Okay. No problem.
Yes.
I will get a reward R based on SA S dash. And I will go to state S dash. Do you agree?
Yes.
Correct. So this now I have this entire thing ready to me. So I started from S. I took an action A based on this policy. I went to a state S dash. In turn, I saw a reward SA S dash. Sure. Now
Yes.
I say that so all of these is known to me. I know the value function at SA, which will be initialized randomly, say initially. I know the value function of SA. I know the reward function. Yes or no? The only thing I don't know, what do I not know? I don't know A dash. So A dash is selected as is the maximum, is the argmax of a QS dash A. Fine. Right. Yes or no? This is the best. So best action, A dash. Best action.
Yes.
I select the best action and then I put the value into the value function and I just get that is the difference. And as n tends to infinity, because we are updating the optimality equation directly, Qn goes to Q star. And you get pi star of S as argmax of A Q pi star of S comma n. Correct?
Yes.
So that's you get directly. But now in this TD learning, since it's a policy evaluation algorithm, you don't get it. Right? So you have to, what you need to do is you have to invoke the policy improvement or the optimality equation. The optimality equation has to be invoked again. So that's the optimality equation again is V pi S star is equal to expected value of reward A S dash plus V pi star S dash. Correct?
Yes. Which is the Q pi again Q pi star of S
Correct.
when argmax.
S
Where that
dash.
many is argmax.
Correct. So you could directly do value iteration here as well. That is also possible. I don't mind. So value iteration is like when you just iterate over stars. So this is another algorithm you will get. Or you could do policy improvement. So policy improvement, what is the policy improvement? You deliberately get the actions, right? So TD learning can also be used for value iteration. See, how do I do value iteration? The same equation I can write. So this is value iteration. Another approach. What can I write? Vn of S, I can write this as Vn minus 1 of S plus gamma times reward of SA S dash plus V pi of S dash. Correct? Yes or no? Or Vn of S n minus 1 of S dash and minus Vn minus 1 of S. Yes or no? I could do that.
Like I have been doing this only to get V pi infinite
Correct.
times.
But the policy we were playing here is not the same policy. That's what I'm trying to say. So the policy is fixed. So here I am saying that pi star is known to me, isn't it? I am saying pi star is
Yes.
known to me, but that is actually not known. We have to find out that pi star and we have to iterate to find out that pi star. Yes or no? So this algorithm will not converge to the optimality. This will converge to the policy you are selecting the action by. You have to keep changing the policy to get to pi star. So how do you change the policy? You select pi star of pi n plus 1 of S as the argmax of A in S, Q pi of S comma A. Q has to be invoked, whatever you do. That's my point. Do you understand? So when you invoke Q, you get the reward S A S dash plus V pi of S dash given ST is equal to S, AT equal to A. This is the problem. So now you will have to see
Yes.
which action gave me the maximum reward based on the policy V. And you will have to take for that action, you will have to select what is the expected value. That is, you have to basically take a Monte Carlo average of this. MC average. Is it clear? That is,
Yeah.
for this reward A, you will select all the possible S dashes and you will keep adding the rewards. And then you will select the best action. Then you will get the best action, correct? So basically, even if you do TD learning, you will have to do steps of improvement using Q learning was what I was trying to say. Okay.
Yes.
So this is normally what I'll get is I will get this equation, which is a update equation, and I'll keep on updating. So policy, if it does not change the policy, you will not get the P pi star. So basically, once we did that, right? So I'll just show you what we had done in value iteration.
Yeah, yeah. Like this is the same kind of uh,
The same kind of.
like in case of MDP, what we did, we are doing the same thing, but here only we are where the reward functions were known last time. Here we are only sampling the
Yes.
reward functions, and
We were only.
everything is based on Monte Carlo.
Yes, everything is based on Monte Carlo. I'll just show you that. I'll just give me a moment. This was before this
Yeah,
MDP
it was in
action.
lecture.
Which one? Eighth.
Yeah, 8 8 years.
Correct. Bellman equation we derived. See, policy iteration we did. We are doing the same thing. We're finding out policy iteration we are doing by first using TD learning to evaluation and then invoking the Q value function as we did here using Monte Carlo. That's it. Correct?
Yeah.
Fine. And there was one more algorithm that we did that was directly, that is this. Fine. That's exactly what we are doing, isn't it? improving the policy directly.
Yes, yeah. So we have in both model and in both model base and model free, we have so far encountered three types of algorithms. That is one where we calculate the first two policy iteration and then do policy improvement. Next, we
Correct.
implicitly change the value function and in the v value function, and in the third, we do the Q value function, and we have found out that the Q value is the Q learning is so far the what's giving us what's most hassle free.
Hassle-free cut is right, but it does not have good convergence results as you go larger into approximation algorithms, for example. So it becomes a hassle then to use Q learning because Q learning does not have guarantees of convergence, unlike these value iteration algorithms. So I made a mistake. This is correct, but this is because we are playing the same policy. We're not going to get this thing. So policy improvement using TD. This is not an algorithm popularly discussed in the field. So this is one of the ideas that I came up with and it really worked. But yeah. Another one is the value iteration algorithm. This will also work. Directly learn the value function, that is v pi star of s is max of. So always remember you have to bring in the max term, q pi of s star. Right. So this is basically the expected value of the reward s dash plus v pi of s dash given s and a. So now this also you can do. Can you tell me how? Even this can be done using model free methods. Any algorithm you have done, you can convert it into model free. Tell me how. For a particular state S, yeah, tell me.
We would just estimate the functions using the all the previous random variables we got, and we just average over the states we got.
Correct. So you go to a state S for a particular state S in a trajectory. So what becomes really tricky over here is that you need to get a trajectory. And then for that particular trajectory, you see the reward S dash. Say you have a trajectory and in that trajectory you have S, you have A and S dash. And you try to find out all those policy, all those trajectory that goes through these. Right? This is what you want. Yes or no? You basically are trying to find out all those trajectories because this first term that you have over here it is an expectation over S dash. Yes or no? This is an expectation over S dash. That is, we need to find many S dashes. That is the only random variable. Do you agree? In the expectation, S and A is given to me. That is already given. So these are constants. Constants. So only expectation I have to find over is S dash. Do you agree? Right?
Yes.
So I will find the expectation. How? I will see all trajectories, passing from S comma A, and then just do Monte Carlo. Yes or no? So, and then you see, just do average 1 by n, reward S A S dash. So you can say S dash I and V pi of S dash I equal to 1 to n. This is all you need to do. And you see it for all actions, and then you select the maximum action. Yes or no? That's all you have to do. So any algorithm that you have the expectation over, you can always estimate it using Monte Carlo is my point. People don't do it generally because the TD learning algorithm is so cute. So nicely you have temporal difference terms as we proved last time. But Monte Carlo can be used everywhere is the big takeaway. Okay. So now the crux of today's session not take much of a time, but is an off policy versus on policy algorithms. So you see in TD learning algorithm, what happens? In TD learning algorithm, the agent needs to play out the policy that it wants to value function to, correct? In TD learning or TD0, if you want to evaluate VPy, which policy do you have to play?
We are going with the selected policy pi, and then we are for finding out the value function, then we are improving it.
That is not, I'm not even improvement, just the TD0 algorithm. In TD0 algorithm, if you have to find VPy, that is the policy evaluation, just evaluation. You will have to sample based on the policy that you select, yes or no? Pi.
That's what I
You,
mean. Yeah.
yeah, you improvement you are not doing basically. We are saying whatever
No.
policy we have,
Yeah, yeah.
correct. Same policy as we want VPy to show the values for, value function for. So therefore it is called, this is called the on policy algorithm. On policy.
Yeah, so we are following the same policy for the entire trajectory. That's the idea.
Correct.
Aim policy.
So
And
there, okay, yeah. So there are two policies here. Now I will tell you policies. One is called the target policy, and then I will explain. Just bear with me. Another called is the behavior policy. Okay, so in the left, you can see you improve and evaluate the policy that we select the action based on, and we and of policy, as you can see, we write it as improve and evaluate different policies. So basically, they're not the same thing that's we're referring to. So let's see what do I mean by that. So the target policy is it is the policy pi such that V pi is to be learned. It is the policy pi if we want to learn or value function V pi. Now, this is called the target policy, whatever we want to learn the value function for. The behavior policy, on the other hand, is called for Monte Carlo or model free methods, we need to traverse the MDP. But in behavior policy, what do? We select the action based on this policy. Just the action is selected based on this policy. Any questions? So there is a very, very big demarcation over here. Why is it important? Now, say you have a TD learning algorithm and you have a policy that never goes into this state, so into this region. So what happens then? So what would happen if you do not explore? No exploration. No exploration. Say, so I will say that I'll show you an example. But say, for example, you start from this state and this policy tells you you have to reach, this tells you always follow this trajectory. But then if you do that in Monte Carlo sampling, these are all question marks, right? Yes or no? Yes or no? So exploration becomes important. Exploration is tough because some policies may not allow for it. Now you may say that, okay, but the policy is good. You are not allowing for it. But what in real life, we would like to have a better model of the world. You are in that policy. You are in those states which are dangerous and you don't have a value function for that. You would not know what to do next. So therefore, we want to do something like we may want to learn this policy pi, but we may want to take decision based on this policy, which is a uniform policy. Do you agree? So this could be our behavior policy. So if we take a behavior policy, so you can clearly select the agent selects action based on the behavior policy, but tries to learn this policy, the red policy. This is the policy we want to learn, and this is the behavior policy beta. At every step, say you take a uniform policy to select where you want to go and so on. But I don't know if I do that, I use the Bellman equation directly, I will be ending up learning out these, right? The value function for this policy. I don't want that. I don't want V beta. What do I want? I want V pi. Do you agree? Clear? But this V, what beta is helping me go to those states and observe the rewards. So beta is helping me go to these unvisited
So are we
states.
doing like an epsilon greedy approach where we are doing selecting actions from beta sometimes and from pi sometimes? Like then
We'll
how?
see that. We can always select from beta and still learn pi, is my idea, is what I'm trying to say. The idea is you can always sample from beta, but end up learning pi is what I want to say. Okay, fine. So let's so clearly the points I was stating. So if you use greedy algorithm, you could have end up while you're being deploying the machine, you could end up in unexpected states where the value function is not estimated. Next, due to the noisy nature of the environment, the agent may initially conceive potentially dangerous states to be rewarding. So this is one of the cases where you noisy rewards you get. Say, for example, people taking wrong decisions in life regarding anything, and they get a positive reward. For example, gambling. So you get a positive reward, but that at the end is not a good thing to do because you would end up losing a lot of money if you gamble. So initially you may get a lot of high estimate, but once you get that, you don't want to just select action based on those policies because those could be potentially dangerous. And you want really a policy that can help you plan and execute actions later on. So again, deploying in real life could be dangerous if you have a policy which actually selects falling off a cliff to learn the value function. Instead, we have to learn the value function of the falling off of a cliff by not actually falling off. So those things have to be really taken into care, and the this behavior policy would help you do all of these. So you can design the behavior policy based on whatever you want. So again, so behavior policy, you select action based on beta. Again, I'm writing it mathematically now. So for a state S, you select action based on beta, you go to S dash and get a reward in between. But behavior policy, but learn V pi of the state. This is what the goal is. Learn this, but actions from here. Let's learn. Okay, so now how do I do this? So we do this by a technique called importance weighting. So what is importance weighting? Is this clear? The concept, the intuition is clear to everyone? Any questions?
Yes, the premise is that in case of the Q learning and the TD algorithm, we were still using a policy and or and updating that policy. Uh, but the assumption that that policy is a safe one, it can be a safe one. And in that case, one might question that why are we going to do beta? But in case the policy is not a safe one, we need to have an idea of what the other value functions are in states we haven't explored, so that
Yeah.
we don't encounter a situation where we fall off the cliff.
Correct. So basically what happens is, even if it is a safe policy and you are just estimating that value function for that policy, we're not basically not giving enough importance to dangerous states if we just want to do that. And potentially that is a bad thing to do. Therefore, we sometimes the exploration itself could be important, that you don't want policies that are you want to learn the value function for a restricted policy, but when you're testing out stuff, you want more exploratory steps. Clear? It could be both ways, is what I'm trying to say. You can either explore more or explore less with this flexibility of the behavior policy. Right? Gives you the flexibility to explore without affecting the learned policy, learned value function v pi of the target policy. Correct? Right?
I
See,
mean,
normal. Yeah.
here the problem we are doing, the assumption is that the states isn't changing and the value function is the states aren't changing, but uh, it might be that like in
Even
a
if it changes, you can do.
difficult problem. Here's the advantage of exploration, that if the states changes, we would be at a better of position to like select an optimal policy back then, and we might avoid like falling off the cliff in a situation where the state space changes if the
Correct.
exploration is smooth.
Yes. You are basically learning the entire state space, the entire state space's value function.
Yes, I think if the when in the grid the value function of a particular cell changes, we would be better off in a better off position to change our policy at that point of time if the states
Correct.
change.
This is the one of the intuition, but basic, yes, that is correct. Even if the state changes, whatever
Yeah,
is happening,
otherwise
you.
there's no point in exploring. If we know if it's a static, we might always explore.
So,
Explore it.
so initially starting off itself, you do not know the value function. So whatever you want to do, if your beta is equal to pi, then it's called an on policy algorithm. On policy, you can do on policy algorithm, but the off policy algorithm gives you that extra, what do you say? The extra tuning parameter in your hand that you can select any policy you like. Clear? That's and the motivation is exactly as you say. And it's also like you don't need not always use it, but both of these are equally used based on the problem statement. Right? Okay, so how do we do that? We do that using this property. Say all this while we are calculating expectations, yes or no? This is what we are doing. We are calculating RL is basically expected rewards, yes or no? This is all what we are doing, correct? There's nothing else, only
Yes.
expected reward. So now I tell you, say your value function v pi of s is nothing but the expected value of gt given s is equal to s. Correct? Gt is the summation of r st plus I at plus I st plus I plus 1. That's it. So, but I am going to tell you that, so no, I don't want to take actions based on policy S. I don't want to do that. I want to take it in some other parameter. So this expectation is calculated based on the policy pi. But I don't want to do this. I want to do it in terms of some beta. Is the exclamatory statement that I'm trying to give you. So how do I do that? So let's try to do it in a simple example. Say for example, v pi, this condensed whatever explanation I'm going to write is given by the expected value of pi of x. So this is the lemma. So whatever value you want to say the for an expected random variable. So say x is sampled by the distribution pi. X is sampled from this PMF. We assume a discrete random variable and say that x is sampled based on this discrete random variable, right? So you can write this as E. Okay. So this eta that I have over here. So what I'll do here is, can I write this in a different way? Is my question. Is the expected value of pi of x? Can I do something about it? How do I write this? Is the expected value? I will write this as x p of x is equal to x. Yes or no? Do you agree?
Yes.
So now this is known to
This
me.
is by PML.
Yeah, this is the PMF, correct. And this is just p of x, correct? Pi of x given to me. Do you agree? This is the
Yes.
distribution I'm given to me. So I will just write this as summation of x to x, x pi of x. Now, so I have written it down, expected value of pi of x. This is what I'm calculating when I'm taking summation of I equal to 1 to n xi, 1 by n. That is all fine. But now I say that no, I don't want to sample by this policy. I want to sample by a policy beta. So what can I do is the step 2, I can do something like this. Same equation I have. Say beta x is not equal to 0 for all x. So what I'll do is, can I do this? Do you agree?
Yeah. So the next step would be to make a pair of x and beta x.
Correct. So I will just do this. So basically I multiplied and divided by beta x. That's all what I did. So now I kept beta x outside and this thing as the function, say f of x. So is this familiar to you?
Yeah.
What I
So
think
we
is
are. This
clear.
is a we are changing the random variable, and when we are now for this random variable, our policy is beta.
Random variable is still x.
Oh,
RV is still x. The distribution
yeah.
is beta. Distribution is beta or distribution is pi. That depends. Random variable is still taking values x1, x2, xn. Same random variable. But the distribution
I
is
mean,
changing
it's
over the random.
changing the expected value of this x phi of x by beta of x.
Correct. So it's changing to expected value of g of x, where x is sampled from
I mean,
which distribution.
this is a function of a random variable x, and like
Correct.
as we done the
Okay, yeah.
previously,
Okay, that is
I mean
fine.
that function is a new random variable.
Correct, correct. Fine. Absolutely right. This is a new function, new random variable. So this is an expected value of g of x, where g of x can be written as x pi of x by beta of x. Correct? Do you agree?
Agreed.
So this is where what you can do. So basically, whatever beta you want to get the MDP to behave as, you can just take the average of, if pi is known to you, xi I equal to 1 to n. This is still going to give you the expected value of x according to pi, where xi is sampled from the beta behavior distribution. Correct? So even in Monte Carlo, if you sample based on the behavior distribution, you're still going to get the same expected value. That's what we are saying over here. Okay. Any questions? So now I'll just show the last thing for today. That is, how do we do it in Monte Carlo sampling? And you can do the same rest. Say this is your value function, correct? P pi of gt. P pi for a particular state S is E pi gt given st is equal to S. Do you agree?
Yes.
So now gt, what does it comprise of? It comprises of st, at. Rewards are deterministic, so I'm not even considering them. st plus 1, at plus 1, st plus 2, all the way to S capital T, at. Do you agree?
Yes.
Fine. Where T is the terminal state. Fine. So very good. So I say that this is essentially the same as, again, by Lotus GT, the probability of AT ST plus 1, AT plus 1, ST plus 2, dot, all the way to ST, given small s small t. Yes or no? For all GTs in G. That's all it is.
Yes.
So this is, since it is over the entire trajectory, I will take that. What is the probability? So this is basically telling me this returns the reward for the trajectory. And this returns me the probability of the trajectory. That's all it is. So now I will try to simplify this, and I will try to see if I can bring in my my own policy idea. Let us try to do that. So AT ST plus 1, AT plus 1, ST plus 2, dot, S capital T. Can you tell me an idea where I can simplify this? Any idea can you tell me? Simplify this stuff into conditional expectations, which I know of. Remember, I know some things. I know ST plus 1 given ST and AT. I know the policy pi. Say this is being according to policy pi. According to policy pi, I know pi of AT given ST. These two distributions I know, right? At least if the model is known, I know it. If the model is not known, I'll see what happens. This is generally the MDP equation, the Markov controlled Markov chain. And this is the policy. Okay, so let us see what I can do. Can I write this as capital ST given S T minus 1, ST minus 1, AT minus 1, ST minus 2, AT minus 2, dot, ST into, what will I write this as? Can you tell me? So I wrote the
Five.
last,
Uh,
yeah, tell me. Into. So I condition everything. All this, I put it in the conditioning variable. So I have to multiply the same things by P of A given B or P of A
yes.
comma C. Do you recall? P of x comma y given z is equal to P of x given y comma z into P of y given z. Yes or no? So I told you whatever is the conditioning stays in the conditioning vector if there is a conditioning, and you can use your same formula of P of A given B is equal to into P of B is equal to P of A comma B. This is the trick that you can use. If you have already a conditioning variable, the conditioning variable remains later, right? So you tell me what 80 minus 1, then st minus 1,
Yeah,
then
then it goes on until when then we only condition with ST because yeah,
correct, small s small
that's our
t,
Z.
correct. At minus 2 dot 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 small at. Fine. So now what I can write this as? Can you tell me? By control
I'll
Markov chain.
use I'll use Markov property and then I'll just make it because I know the probability is P of ST plus 1 given ST and AT equal to a given
Yeah,
action. So we'll just omit the part from ST minus 2 as you have already done that.
correct.
Yeah.
Correct. This is independent given st minus 1 and at minus 1. Control Markov property.
Yeah. So I get the idea now. So first, once we are gonna get the probability function and once we are gonna get the policy function. When
How will I
we
get the policy function? Can you tell me? In the second
because in the
equation,
next
very
step
good.
we are right PAT minus 1 given ST
Okay,
minus
very
1
good.
given
Given
ST
st minus
minus 1
at
equal to
minus.
small. Yeah, AT minus 2
You're
and we are
very
gonna
good. Very good. I'm very happy. Very nice. Very good. So st minus 1, at minus 2 dot 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 at given st. So this
yes.
becomes, so this is all again independent of all of these.
Yes, we are going because this is after all a Markov decision process. We are gonna use the Markov
Yes.
property and
This is not a
say,
Markov property. The action, the idea is action is selected only based on current state.
yeah, sorry, there's no Markov
This is not
property.
a Markov property. This is the action is being selected based on the current state only. So you get pi of at minus, don't be sorry, it's fine. At least you're saying st given st minus 1, at minus 1. Okay, so now I have the entire term st minus 1, at minus 2, dot 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 at given st. Right? So now you see this term again, it becomes by induction the same problem. Same problem. So I can write it as induction I equal to 0 to t minus 1. I don't know if it is 0 or 0 not 0, but let's try. St plus I plus 1 given st plus I given at plus I pi of at plus I given st plus I. Do you agree? Did I made a mistake?
No, in case of the left
Correct. T
equation,
minus 1 will
it's
come
all
here.
right.
There's no t, just I, na? Sorry. I plus 1 given I.
I mean, we were starting off from a tier, I think, but it's
Yeah,
all
yeah.
fine. The idea is,
Yeah, yeah. Correct only, no? From t. It's starting from t.
yeah, yeah.
Correct.
You had written starting from I equal to 0 last time, you changed it I equal to 3, so it's
Yeah, that's it. That's it. Yeah. Fine. Fine. Correct. This is great. So this is for a policy, the expected value of GT given ST is equal to S and a policy pi. So now similarly, you can write expected value of GT given ST and a policy beta. What will it be? Pi I similarly I equal to 1 to T2, T minus 1, Si plus 1, Si, Ai by beta of Ai by Si. So basically, what happens over here is you have these two properties. So this is not expected value, sorry. This is the probability of the path. The probability of St to T and At to T given St and pi. Yeah. Correct. St and pi. And this is probability of St
Because
to
if it
T.
would have been expected value, we could have equated it and then we would have gotten an inequality. Right.
Correct. No, that is also fine. And beta. This is fine. So what I'm trying to say to you is, see now beta, right? The expected value of GT given ST and a policy pi can be written as GT's GT into the probability of ST to T, AT to T given ST and policy pi. Correct? This is exactly what I can write, and I can divide by probability of ST to T, AT to T, ST and given a policy pi and given a policy beta, and I might multiply it by ST to T, AT to T given ST and beta. Do you agree? Fine.
Yes.
So this thing again, this ratio, I can simply write this as, say it's rho of T can be written as pi of I equal to 1 to T, pi of AI given SI, capital T, sorry, beta of AI by SI. Do you agree? Fine. So basically this equation turns out to be the expected value of rho T into GT given ST and a policy beta. Yes or no? Correct? Where A's are
Yes.
selected by beta. So you start off by A's are being selected by pi by just by multiplying by this importance factor. You have a total control over the policy beta, which you can clearly select and just multiply this term given to you. That's it. So now can you tell me the algorithm how to do it? So currently I know that these terms are there with me, but in real life I will have to do a Monte Carlo. Yes or no? Right?
Like for
I will
the
have
policy.
ST. Correct. I will have ST, I will have AT, ST plus 1, and I will go on till S capital T. Correct? Do you agree?
Yes.
So now say T equal to capital T. So I will get V pi of S capital T is equal to 0. Yes or no? Correct?
Yes, it's a terminal step.
Okay. Now for T equal to T minus 1, what will I get? I will get V pi of ST minus 1. So always remember in dynamic programming, you turn from the terminal state and then you go backwards. ST minus 1, what will I get? I'll get V pi of ST plus GT. Yes or no? Which is basically the reward from ST minus 1, AT minus 1, and ST. Do you agree? Fine. Do you agree?
And
Questions?
uh, I mean, I guess it's a bit unclear.
Okay,
It's
I will write it instead of writing GT, let's write capital GT. Fine, at terminal state T, this is 0. Do you agree? The gain reward. So GT, G small t is what? It's a summation of I equal to T to capital T of R, I, AI, I plus 1. Yes or no? Do you agree?
yeah.
Fine.
If the initial state is the terminal state, then there's no reward.
There's no reward, 0. Okay. So now I say that G of T minus 1 if I have to find. So what will I do it write it as? I will write it as G of capital T, the final state's reward, plus the reward I get to reach that permanent state. Do you agree?
Yes.
Fine. So, but now what is the action AT minus 1 selected as? It is selected as beta of ST minus 1. Yes or no? But we want with respect to what? Tell me.
With respect to pi.
Pi. So I will just multiply this important stuff pi of rho of, what will it be? Rho of T minus 1. Yes or no? Which is basically pi of AT minus 1 given ST minus 1 by beta of AT minus 1 given ST minus 1. Do you agree? Yes or
Yes.
no? Okay. If you agree to it, now next what do I do?
So we are starting from the terminal state and we are choosing the action from beta because if we had done pi, then we wouldn't have been able to go back. Right. So we are doing select
Correct.
first. First we have to do it from beta because otherwise we won't be able to go back from the terminal state.
Correct. We can just start from T and then we can keep on going to the left to back, right?
Yeah. Okay.
So now what I'm doing is I have this counter with me, right? Yes or no? I have this counter ready with me. Fine. So what I'll do is say I will say GT is equal to 0. Do you agree? I can write this base
Yeah.
case.
First step we initialize GT equal to 0.
Correct. Now for T equal to T minus 1, T minus 2, all the way to small the T, whatever we are trying to do, or is 0. Correct? For a trajectory, for one trajectory. This is the trajectory. Repeat for all trajectories. For all trajectories. So say for a current trajectory, you get this, right? So you have T equal to, now what do I say? I say that G of T can be written as, what can I write this as? G of T plus 1, right? The next state's probability plus the reward. Yes or no? ST, AT, ST plus 1. Yes or no? Fine.
Yes. Yes.
Good. So now for the T minus 1th state, what will I write? For the T minus 1th state, GT, what should it be like? So for T minus 1 state, then T minus 2 state, and so on. What will it be like? So it will just be what? It will just be the summation of whatever you receive. That's it, isn't it?
Yes.
The reward is what? Yeah, go ahead.
Yeah, like we are in this case, instead of like for all this while we had been calculating the GT in a forward manner, but here we are backtracking. So we are considering the reward at each step that we got from getting from T minus 1 to T. So that's what we are gonna add to get GT minus 1 and then
That's
GT
it.
minus.
Correct. Correct. So basically at this particular state, whatever GT you got, GT equal to 0, you will just, so what is what is the equation? The equation is expected value of rho of GT. Yes or no? Rho T of GT.
Yes, because
Correct?
now because we have our main goal is to also use go off policy sometimes, so we have
Yes.
to use the
Multiply rho T.
routing.
Then how do I get rho T? So initially rho T will be 1. Do you agree? Because for the terminal state, it doesn't really matter. We have to do something to actually, for every other state,
Yeah.
we have to keep on
So
multiplying.
yeah, for a
So I will.
given trajectory, there has to be a given policy which will take us to the terminal
Correct.
state.
So for example, let us look at this. Let us take a terminal V pi of st minus 1th case. What will it be? This will be V pi of st. So this reward function plus the reward of going from t minus 1 for an action t minus 1 to st. Do you agree? Into the policy pi of st minus 1 given st, given or at minus 1 given st. Do you agree? By beta of at minus 1 given st minus 1. Do you agree? Fine. That's
Yes.
exactly, this is what I will write. This is rho, this is your GT, and this is your rho T. So now tell me, how do I write down the recursion? That's all I need to know. Very simple, no? So I have, so this is 0 to me, and I know this reward is given to me. I will just, what will I do?
I mean, I have
Multiply
to
the,
wait with the pi function, but when f of t, but for before that, I need to calculate the f of t. So uh,
correct. You can do rho T is equal to rho T is equal to rho T plus 1 into, this is rho capital T is 1 into pi of at given st by pi of
by
at.
b no beta. Wait,
Yeah,
beta.
beta of st. Yes.
Yeah, yes.
And I
So
just
this is
multiplied
the
over.
recursion. Yeah, this is the recursion,
Yeah,
and then we get it from
correct. So
yeah.
this
Then we
GT will be appended to V pi of ST, right? And then for all take average of, so you store all the V pi of STs, store all the V pi of ST at the end, and just add, take the mean. Right? Clear?
yeah okay.
That's all you need to do. Basically, just I was just telling you how to code it down. Any algorithm you code in the similar manner. Finally, so model free algorithms done. So Q learning is done. So now is it, now tell me, is Q learning a off policy or on policy algorithm?
Q learning is on policy only because when we are not using beta anywhere, we are not going like we are just updating the policy all the time. So we actually don't have a like a static policy. It's git
We,
we are implicitly learning the policy.
there it
It's-
is an off policy algorithm. Why see?
Yeah, because we are implicitly learning the pi and we don't know a deterministic pi.
Not
But
because
in
of
case
that.
of
That even if you were evaluating and improving the policy, eval and improve same policy is still on policy. This is because of this action selection that is selected as the maximum, right? Which is not, which is never the same, other than when you reach the terminal condition, right? this is not based on current policy. Understood?
Yeah.
This is
Okay.
why it's
So
called an off. Yeah.
got it. So both like policy improvement and this part here, it's of policy
Correct. It's off
because we are
policy because you are taking an
but
action based
for
on a different policy. That is the maximum
different
policy.
policy, but policy only policy iteration is a non-policy approach. But
Correct.
here Q learning is an off policy because of the of the max of this argmax
Correct.
function, which is what makes it the off policy.
Correct. So there is a on policy variation of this called the SARSA. What you end up doing is I told you once about the SARSA, but you replace argmax of A prime in S dash by just S dash comma A dash. You replace this as Qn S dash A dash, where A dash is selected as still the policy. The same update rule, you select the action based on the same policy. It's called the on policy algorithm. On policy algorithm. To be clear, you start from a state S, start at S, select action A based on pi of S, observe reward R, go to next step, state S dash, and select A dash based on. So this is called a SARSA algorithm. SARSA. This is why it's called SARSA, right? So here you see your both, if you select an epsilon greedy policy, your both AT and AT plus 1 are selected by the same policy. But in Q learning, this is different. You select this as argmax of A in S, Qn of S comma N. So if you select an epsilon greedy policy with an epsilon greedy policy, you can clearly see that both A and AT plus 1 are the same policies, but for Q learning, they are not the same. People also do what is called as an expected SARSA to minimize the gradients. So in expected SARSA, what you do is instead of just selecting one action, you replace it with the expected value over all actions. Right? This Qn pi of A given S dash, Qn of S dash comma A dash. Fine. So see, this is just one value, right? So just one action. So we'd say that just selecting in SARSA, just selecting one action may be noisy. So instead of just what we do is you take an expected value of all actions in the state, and that also converges. One action is just an unbiased estimator. Unbiased estimator means when you take an
I got
expected
that,
value of
but
this. Yeah. Tell me.
uh, I mean by expected value of the action. I mean this probability of that I'll select A dash given S dash. Uh,
Yeah.
I mean that's gonna
See,
yeah that
first we
can
replaced max of Q of S comma A dash.
yeah that this was deterministic because this was going to be a
Correct.
particular action for a given state. But
Perfect.
now shift to
This
the
stochastic
on
case.
policy, the previous policy that we were doing. But again,
Correct.
I was going to tell you when you were saying explaining, but uh, as you said, there's no we would be only following the pi and there would be no exploration and we won't be actually updating the pie. So we'll end up with we might end up with a very bad policy because we are stuck to the initial policy and we don't know if that's a good policy. So that's
So
what going
we're
to cause
actually
noise.
not stuck to the policy because see here the expected thing is all clear, right? So I just what I wanted to say, this is just noisy. So we convert it into, we'll see next time what is stochastic gradient descent, but we convert this into the expected value of UN in expected SARSA. That is fine. What I want to say here is look at the epsilon greedy strategy that I'm taking here. I am selecting 90% of the time, say the optimal policy. So that itself will be invoking the Bellman optimality equation, and I will still explore.
Yeah, like you have defined the policy in such a manner that it would invoke that.
Correct.
But
Correct.
if in case I stuck to an initial policy where I wasn't
If you
exploring,
select the base same policy, you will just select Q value function
yeah,
for that policy, right? That's what you do.
yeah,
You will not be
yeah,
you will not use the optimality equation.
right,
But SARSA
right.
algorithm, if even if you do that, is shown to converge. That's the so RL has all this algorithm which converges. So therefore, it's basically better to take an epsilon greedy because we can clearly see it. When we do not do that, we generally end up getting policies that we can really not explain well. But that's also another thing to try out, like selecting an uniform policy, for example. If you select an uniform policy always and evaluate this, you will get the Q pi of that, right? Isn't it?
Yeah, essentially we are going to get the q pi of that function and
Yeah.
we
Let
won't
us see
be
what
using any optimality there.
it's a
Going
good
for any
question. Let us try to solve it. R of S A S dash plus V pi of S dash into this is exactly what will happen. I think you saw this. So expected SARSA will do this. So this is how expected SARSA comes about. Good, thank you for asking. This is basically the expected value. If I take the expected value for all the policies over in S dash, I can just write it as Q pi of S dash comma A. Yes or no?
yes.
See, very good. I am very happy. This is you're actually observing these things. So this is now you have this. So you have the update, right? Qn plus 1 SA is equal to Qn of SA plus gamma alpha times R SA S dash plus the expected value of Q pi of S dash A. This is really what I had not thought about, but ended up doing it. It's really nice, very satisfying. See, so this is the update rule of expected SARSA, right? This will converge to Q pi, not Q pi star, correct?
Yes. If there was no
Change in the
exploitation.
policy, correct. No exploitation, it will converge to Q pi. Fine. So I hope you see, I don't have time to discuss the TD learning algorithm today. We'll start with the TD0 code next time.
Okay. So
If yeah. So
yeah,
I could
I
have done.
asked so many questions.
No, it's fine. It's like I think today's session was very interactive. It was really nice. So especially the last thing that came out that the expected SARSA is exactly where the SARSA comes from. It's really nice. So always try to get back to the basics, and I think you'll get things cleared up fast. So I'll stop recording, and if you have, I'll discuss a few things offline and then we'll stop.